Okay, in the last week we have seen that in reliability and also in safety relevant situations, human factors are very important. One of these things is labor safety, the other is safety of technical systems. And besides, let's say, chains of events and dependencies like fault trees and chains of failure causes and failure effects, there are also surrounding factors which increase or decrease the probability if there will be accidents or safety relevant incidents. In order to make life safe, there is not only reliability, as we have seen. Generally, the basic aspect of quality is relevant, and in order to provide a good quality of the product or of the service, it is also important to have good organization, and that means the organization must be organized in a way it can provide good quality. And one of the most important standards which describes such quality matters is ISO 9000. We will not go into the details of this. This also has been treated, for instance, in the bachelor program, in the quality management lecture. But ISO 9000 describes how, let's say, good organization must be organized. And one of the things is we must not have unclear or diffuse responsibilities. So it must be absolutely clear who is allowed to give instructions, to give clearance for something. That may be actions, but that also may be, for instance, documents. Yes, if you have an internal document on safety, like for instance a document in combination with Corona, then it must be clear who is allowed to give such instructions, to implement it, and further on to give to assign responsibilities. Let's say we have the president of our university, the rector. He is in charge of the whole organization, and he can give Corona instruction, or in German it is Verordnung, which is some kind of law which is not passed by a parliament but by some other organization. So such a Verordnung can say in order to provide actions on a lower level, the dean may be responsible then. And the dean says the dean of academic affairs is responsible for organizing exams, for instance, in that. So that means we must have very clear responsibilities, and we also must have very controlled information flow. Yeah. So how information will be flowing must be provided, or there must be a rule for information flow. And of course, it is always important to have more information than too little information. Of course, an abundance of information is also not good, because this abundance of information can hide the relevant information. Okay, and A third aspect in such quality management is that, for instance, safety or quality personnel is not independent and on a too low level in the organization. So that is important. If there is some engineer who is, for instance, safety engineer, it cannot be he has a superior who can give him instructions which are against safety rules. So if he would have such a boss, then question would be whom to obey. Obey the rules and the Verordnung, or obey your boss, yes? You could also argue the boss, by giving this instruction, he take responsibility now. But that is not wanted, yeah? Because we want to have a clear responsibility, and people who are responsible for some fields which are of high importance must be independent. Yes, we have controlling in companies which is independent. We have so for financial affairs we have quality engineers which are independent. We have safety engineers which are independent, and that is important. But one is you can claim it, and the other thing is it really implemented in that organization? So if these provisions are not given, then the danger of having safety hazards or quality hazards is increased significantly. You can prove this by the fact that after such actions have been taken, quality and safety generally are increased significantly. Then generally ineffective technical activities, superficial safety efforts or safety cosmetics, so just on paper but nobody really cares, insufficient risk control, risk displacement. That means, okay, the risk is not here but elsewhere, or you say the financial risk is not with us but it is with the insurance, for instance, and that's a reason why we do not take too tight actions, because that would be costly, and it's better in case something happens, the insurance will pay. Of course, they will try not to pay, but such a strategy is sometimes found. Wrong concepts or designs. That means something maybe not state of the art. Of course, you can still find sometimes designs which are not good. Also, some people I heard which said it is not good that, for instance, engineering in big organizations is structured too fine. So the individual engineer only sees a very small part of his work, or for instance, an engineer does only computer work, CAD and simulation, but he has no idea, he never sees the real product, for instance. Yeah? And that's also a big disadvantage. So everybody tries, or possibly tries his or her best on her limited field, but the whole system is not treated in an optimum way. Okay, safety installations based on wrong assumptions. I gave you the example of that safety valve, and the toggle had an indication lamp, and the indication lamp didn't show the state of the safety valve, but it only showed the state of the switch. Yeah, so that's a wrong assumption then you can take here. Complexity is increased by safety installations. There's a very famous image showing a very small system and having safety installations which are 10 times larger than the initial system. In hardware, that is not so good. In software, we can find it. For instance, control software, according to that safety standard 26.2, is in such a way. The safety part of that software is bigger than the control part of that software. So that cannot be avoided in all cases, and if you have an additional safety installation, or if you have redundancy, you do not just double the effort, but you more than double it, because you also have some voting installation or something. So complexity increase is something which is a matter of fact when you have additional safety installations. Missing evaluation or recognition of changes. Yeah, there is something which concerns me a little. Normally, we will see how processes are of getting some safety relevant software cleared. So you design it, you get clearance, and later on you must make sure that nothing is changed here, because all of the risk analysis has been performed on that original software or original system. Now, the trend evidently in modern cars is you upload a new control software to the car all of the time. Yes, it can be when you go to the tool shop, or it can happen when you are just in your garage and the car is hooking up to your LAN, for instance, and uploading. So if it is something on your smartphone, I would say it is okay, because it is not safety relevant. But I really have doubt if such a strategy is really correct when you do it with safety relevant systems. Because when you change the software, normally you would have to go through all of that V model validation and verification process. Okay, so missing evaluation or recognition of changes. Yes, for instance, there is something quite simple in former times. When you got instructions for a bigger system, you had a ring folder, yeah? And so when you got a new part for your machinery, you got also a new sheet for your ring folder, and so your instructions manual had to be updated in accordance with the update of the machinery. It is similar in aviation. For instance, if you have a small aircraft, there is sometimes a change, either a change just in the design or in some regulations, and always the documentation of that aircraft must be updated. So there is a clear process to implement changes. Change management is something which is very important. But all of these are maybe strategies which are state of the art in industry or in organizations by state, and we will not be able to go into the details of these. What can we do against the information deficit? There can be systematic information collection and recording. That is, for instance, also necessary according to law. If you have a medical product, the market must be observed, and if there are complaints, these complaints must be collected, and actions must be taken according to these findings. Unfortunately, and that is again a deficit, for instance, in German state or general in European legislation, if, for instance, a company misses to collect such information or to act accordingly, nothing will happen. So that's a clear deficit. In principle, something would have to happen, but in reality, evidently, often nothing happens. Comprehensive safety circles. Okay, we have seen how FMEA is organized, and in a similar way, we could also maybe take risk analysis and safety analysis on a larger scale than just FMEA. And what is also important, that the information is utilized. So you cannot just store the information in some computer file and then nothing else and hope someone who searches for something will detect it again. But there must be, for instance, some clear management how relevant information is distributed to all who are concerned. Okay, so that is important, and all of that has to be seen under the scope of the quality management of a company, not only under safety aspects. Now, one of the earliest and almost most severe incidents in nuclear power stations was in 3 Mile Island in America, where almost a nuclear power station blew up. In fact, it was just avoided, and that was roughly, let's say, 8 to 10 years before Chernobyl really blew up. And here, afterwards, the behavior of the personnel who were in the control room was investigated, and generally it was investigated how people behave and how people do mistakes. Of course, making mistakes is very much person dependent. It is also dependent on the cultural background. For instance, I see very many protocols and let's say for lab courses or so, and for instance, I can clearly say from let's say some cultural circles, people are more sloppy or less sloppy in writing their protocols, and that means the background and the education and generally how in a certain group such things like precision, accuracy are treated are different, of course. Of course, in a highly developed country, we cannot accept such a thing, but we have to look at persons according to, let's say, our standards in culture, education, background, technical training, and so on. But generally, you can say if some actions are taken, a typical or a standard action is taken, a general omission error is in the percent region. If it's a procedure, there is typically an error in 3% of all cases. Of course, in a procedure, you have many steps, and in these steps, of course, by having more steps, the probability that one step of these will be wrong is of course higher. So the rule of thumb here given is 3%. Let me give you an example. When you are a private pilot, so you fly a small aircraft, let's say a single engine aircraft, and you go flying, you have a certain procedure. That procedure starts from when you sit into the aircraft, you start up the engine. Even for this, you need a certain procedure. You have a procedure after starting up. You have a procedure before you take off, from ground, and so on. And each procedure consists of maybe 5 to 10 steps. And if you normally you must learn these steps, and these steps are individual for each aircraft type. Yes, a Cessna has another procedure than a Piper or something like that. And in that way, of course, you cannot go through such a procedure from memory, because then it is quite sure you will make a mistake. So you take so-called checklists, and then you go through these checklists and say, okay, before starting up the engine, I have looked that there is nobody standing near the propeller, for instance. Yeah, and in that way you go through the procedure. But anyway, even in such procedures where you have a list in front of your nose and you read what is the next step in the procedure, even then mistakes are made. So human actions always have, there will be some errors, and that is 3%. Also, maybe reading something has an average of 3%. So, for instance, let me say, someone in my family, when I'm giving, for instance, the account number, I always repeat it, because I know there were always 2 digits mixed up or such a thing. Yeah. So generally, just reading a data, there will be errors. Calculation error despite a checking of the worksheet. Okay, that's something. You have a sheet. You should work according to that sheet. But anyway, mistakes are made. Now, also in times when, let's say, automatic testing was not so important, we had manual testing. For instance, in some equipment, some parameters were tested, or a good example, still complex printed wiring boards are watched. So some people have a look at these boards. They look at the boards whether all solder joints are okay. You can, even if there are 1,000 ones, you can see it quite good, yes. But on the other hand, maybe it's a percentage which are missed, yes. For instance, you have a missing solder joint, the board is looked at, and then most of the missing solder joints are found. They are reworked. People having a soldering iron will attach that missing solder joint. But if it's a safety relevant device, for instance, a second person should watch, yeah? Or another example, all tires are X-rayed in order to find out if there is some delamination inside or such a thing. And if it's really relevant, it is tested twice. But the second person, or generally, if there are two controllers and the first controllers knows there is a second one, always the redundant person becomes sloppy, and the probability of error is increased. So people have in the background of their brain, they have a thinking, okay, if I don't find it, someone else will find it. But let me say it that way, what is the probability you will miss the defect? Of course, it is 1% when each person has a probability of 10% of missing it. Okay, that could be a small question in the exam also. Omission of a status check when a system is taken over from a previous shift. So that is often in chemical plants. Some people go home, maybe at 3 in the morning, another person comes. Normally, the other person should check from the beginning if every instrument and every indicator is correct. But again, that is not done properly in all cases because people think, okay, machinery has been running properly, so I can be sure there's nothing wrong. Okay. That means people do errors and they are sloppy, and at least we have a certain probability that something can go wrong, and normally we are talking about 99% or 99.99% and so on, but we see here the error probabilities are high, and and here we have let's say reliability data of 99 to 90%, which is not so really high. If the person is under high stress, in a dangerous situation, under time pressure, or sometimes people don't feel well, they are sick or something, error probability can go up to 20 to 30%. In an extreme situation, it can be that the error probability can be up to 100%. That is especially important if several actions have to be taken together, then the probability of a mistake will be quite high, especially in the first minute. So that was the situation in that nuclear reactor when it almost blew up. After the alarm was ringing, people were quite confused. So later on I think it was recorded somehow how they acted, which switches they set and so on, and there was lots of things wrong. Even within 5 minutes it can be up to 90%, but if people survive the first half hour, their error probability will go down. Probably their adrenaline will also go down, because normally human nature is when you come under stress, you get adrenaline, and adrenaline has only one function. It's some kind of supercharger for the energy of your body, but it's not a supercharger for your brain, yeah? And in that way, you can run away faster than without adrenaline, and maybe you can also fight in a more fierce way than without adrenaline, but that's it. Also yes, and in that way, when that level goes down and when people have time to think about the situation, their error probability will go down to a quite normal level, and people can rethink the situation if they are given the opportunity, and in that way the error probability can go down. So of course, when you do the safety judgment of a complex system, it is important to take into consideration that human behavior cannot be treated in a constant way. But human behavior is dependent on the person's background, on the constitution of the person, and on the situation and in which time slot of the situation people are. And of course, that makes it quite complex, and of course, safety engineering for situations where people are strongly involved also involves psychology. Okay, but this lecture is only on technical matters. Okay, so now we have seen the certain concepts. What is reliability? What is reliability in mechanical systems, in electronic systems? What is safety? We have seen that the development of failures, but also the development of situations must be analyzed both in a quantitative and also in a kinetic way. Kinetic means over time. And also we have seen certain concepts to come from a risk to a risk management. And now I would like to give you an example of how people deal with the situation in medical devices. In former years, I was having more emphasis on this part, but as most of the students now are not so much involved in medical systems, but many are also from or are more interested in other applications. I will just give this in a short way in order to show how the thinking in that industry of making medical devices is. So now let's have a look at the law. Anything which has to do with the market is under the legislation of the European Union. So in former years, let's say still 30, 40 years ago, every country in Europe had her own regulations for the market, and of course all standards, and I mean not only reliability standards, but all standards were country specific. And the European treaties provided that the market in Europe has been treated as a whole, and of course also the safety of products is market relevant. Also legislation on safety had been used in former years just as a policy to keep competitors from the national market. Yes? So you had other safety standards for medical devices, let's say in Germany and in France, and so French manufacturers were kept from the German market and German manufacturers were kept from the French market. And okay, in order to avoid this, to say we have a bigger market and in that way we have better competition, more competition, that also will be better for the consumer. and so we have European directives. A European directive is something, it's something like a law. Directive is something which is written, let's say, on paper, like a law, but such a European directive has still to be implemented as national law. And under all circumstances, it must be avoided that such national law is against working against, for instance, freedom of market and such aspects, or leading to lower safety standards than in other countries. And in the case treated here, we have the active implantable medical devices. So what is it? The classical device is a heart pacemaker. We also have another directive, Medical Devices Directive, that are medical instruments and instrumentation used, for instance, in the lab. And we also have something special on in vitro diagnostic directive. So in vitro means you have it in glass somewhere, because you often have glass instruments, contrary to in vivo, which is the implant. So, but we will only deal here with this implantable devices. The rest you can look up. You can also find these directives at the internet pages of the European Union. It's not so easy to find, but probably Google will help you here. The directives, they first define the essential requirements that devices must meet before being placed on the market. That is not just safety requirements, that is all requirements. But because when you have a pacemaker and if you have a implantable insulin pump and you maybe have a brain pacemaker, if you got Parkinson or something, you always have a different device. So these requirements are not written in a device-specific way, but they are written in a general way. So that is something, some properties more on a meta level, which have to be provided by all devices. That's one thing. You must write down what the requirements are. The second is who will check that these requirements are met? How is it checked? Are there organizations? Is there a certain procedure? And so we have to establish conformity assessment procedures. That is something important. There are several possibilities. For instance, with your car, you have to go to the TÜV or DEKRA to have it checked. But there are even some, let's say, assessment procedures where someone can assess something for himself, or an organization can assess it for herself. Then the third thing is to create mechanisms available to national authorities to manage implementation or to intervene on the market. Okay, let me say it here. For medical devices, we have to do a conformity before they come on the market. That can be an organization like in Germany, Technischer Überwachungsverein, or in America it's under the supervision of the FDA, Federal Drug and Food Administration, and so that is before it comes into the market. But there must be also mechanisms, when it's in the market or when something happens, and in that, and for instance, If it's found out a device is dangerous, who will act then? It will not be the same organization like it was before it came into the market. Normally here afterwards, it is organizations by the state, for instance in Germany for medical devices, something like the Regierungspräsidium, or in the case of food, it is the city of Freiburg. These directives, as I said, have to be transposed to the national laws of the member states. That transposing is called harmonization. So, in German, when a law is harmonisiert or harmonized, that means it is transferred from the European level to the national level. But we have also seen, for instance, we have standards ISO-EN, then the standard has been transposed from the international, worldwide level to the European level, and that is also a harmonization. Okay, now essential requirements. Devices must be designed and manufactured in such a way that when implanted under the conditions and for the purposes laid down, their use does not compromise the clinical condition or the safety of patients. That means, first of all, it is described. What is the condition of operation? What is the condition inside a body? What is the condition of the person? Is it, yeah, there can be differences. And what is the purpose of a pacemaker? What is purpose of implantable defibrillator, and so on. Okay, that must be first laid down, and of course that is part of the specification. Of course, that specification must be validated. So it is correct, complete, free of contradictions. The use does not compromise the clinical condition or the safety of the patient. That is nothing absolute. There can be a certain risk. It is important that the risk is, or the danger is lower than the risk when you don't implant that device. That means if you don't implant, let's say, a defibrillator into the heart, then at some point of time the heart will stop working. So it is relatively sure the patient will die within a year or so. So if you do not implant it, on the other hand, of course, implanting such a device is always the risk, the operation, but also the operation of the device. Then you could say the situation is improved significantly, and so that condition is met. So that must not be seen in an absolute way, but in under the aspect of the improvement you get for the patient. But what is never allowed under any circumstance is that by improvement of the situation for the patient, you compromise the safety of another person. Yeah. So let's say something maybe not so serious, but the surgeon could get an electrical shock when he implants it, and so you would say 1 promille of all surgeons will die during the operation from electrical shock. Yeah, such a thing could not be accepted. Yes, even if you would save all of the patients. So that is nothing that can happen. So they must not present any risk to persons implanting them or other persons. For instance, pacemakers from Soviet Union, maybe 20, 30 years old or so, can be risky because they have a plutonium battery. So if these get leakage, plutonium can go out, and plutonium is a deadly substance, even if you just get 10 to the power of minus 10 or so grams or kilograms from this substance. So that means no other person must be harmed. Second is, you have the conditions and purposes. We talk about the performance of the device. So also that must be described. You have the functions, and of course you also must know what the failure of these functions is. So performance, where is performance described? Again, it is also a validated spec which is relevant here. That means, again, what is the voltage that device must have? What is also the time for which is designed, and so on and so on? What is the size? And in that way, there is the specification, and it must be proved that the devices are suitable for the functions. You do not just specify it, but afterwards you also have to check suitability, and that is, of course, the verification. Again, I think the V model is something which is very important: validation and verification. And we can find that V model again here in that legislation or the European directive. The characteristics and performances referred to in sections 1 and 2 must not be adversely affected to such a degree that the clinical condition and safety of the patients or other persons are compromised during the lifetime of the device anticipated by the manufacturer, where the device is subjected to stresses which may occur during normal conditions of use. Okay, that sounds very simple and short, but in fact, sorry, I have a problem now. Do you still hear me?
Yeah, we can still hear you.
Do you also have a green screen now?
Yes.
Strange thing. I don't know what happens here. I think I have to go out.